Hey all dear students, let's see this question of JEE Advanced 2021 paper 1 from Electromagnetic Induction. As you can see here in your screen, the question states a long state wire carries a current I is equal to 2 ampere. A semicircular conducting rod is placed beside it on two conducting parallel rails of negligible resistance. Both the rails are parallel to the wire. The wire, the rod and the rails lie in the same horizontal plane as shown in the figure. The ends of the semicircular rod are distances 1 centimeter and 4 centimeter from the wire. At t is equal to 0, this semicircular rod starts translating on the rail with a velocity v, 3 meter per second. A resistor R and a capacitor are connected. R is equal to 1.4 ohm and capacitor as a capacitance C0 is equal to 5 microfarad connected in series between the rails. At t is equal to 0, capacitor is uncharged. Which of the following are correct? So there are four options. In the first two options, we have to find about the currents. In the second, fourth, we have to talk about the maximum charge. So basically, we have to find two things. What is the maximum current through R, and what is the maximum charge on the capacitor? So let's go on the next page. On this page, I have written the value that was given the question. So first we will find the motional EMF developed on this moving semicircular rod, and to find that I want to assert that whatever is the EMF induced, that will be same if in place of that rod I have this straight rod like this. In place of that semicircular rod, if I replace this with a straight rod which is perpendicular to the parallel rails. And why is that? So suppose I take this one single loop of semicircular wire and this straight wire, as this translating along this direction, so obviously area is not changing, and in going along this direction, so total flux will not change. If it goes along this direction, so B will change, flux will change. So total flux on this loop is not going to change. So net EMF on this loop will be 0. So if the EMF along this is even, so EMF along this will also be even, so that according to KVL the net EMF 0. So whatever is EMF here, that is the same EMF here, and for the simplicity I have easy to find EMF on this part. So for that thing, let me take element. Suppose I am taking an element of the rod at a distance say x from the wire, and here this is the element, and this element is obviously of length dx. This part is of length dx, this part, and on this part the magnetic field is say B. So B is equal to mu naught I by 2 pi x, and on this part, because this is like a rod translating in a magnetic field, so there will be EMF in use, and for this part, this is so part that I can think of a uniform magnetic field. On the whole rod, B is not uniform, so I cannot directly use the formula for the motional EMF. So what I have to do, I have to find the EMF induced on each little part. So on this part, the positive will be towards V cross B, that is along this direction. So on this part, so suppose the little EMF induced is say dE, this dE. So value of dE would be VB into dx. So dE is equal to V, local B there is mu naught I divided by 2 pi x dx. So total EMF induced is equal to V divided by 2 pi mu naught I and dx by x. And for the whole rod, this x varies from 1 centimeter to 4 centimeter. No need to convert in amperes because that will become a ratio. This will go from 1 to 4. So that is V mu naught I divided by 2 pi, and this will be ln x, 1 to 4 ln 4, and ln 4 I am directly writing 2 ln 2. So this 2 gets cancelled, and let me put the values. V is 3, mu naught is 4 pi into 10 to the power minus 7, so that is a 4 into 10 to the power minus 7. I is 2, ln 2 is 0.7. So that is how much 12 into 2, 24 into 0.7 into 10 to the power minus 7. So that will be, so 16.8 into 10 to the power minus 7 volt, and that is what the EMF, and it is a constant EMF. So now I will use this thing for the next part. So now let's go to next page. So I have calculated here the EMF induced on this rod. Total EMF is this. The same EMF will be on the semicircular part. So here the EMF induces E, and that is a constant. So basically now what we have got, and the value of E that I got is how much? 16.8 into 10 to the power minus 7 volt. So basically this thing is a kind of this circuit. So this is a battery EMF, and then there is this R, and this is C. So this is a kind of a charging of a capacitor circuit. So this is C naught. Initial the charge was 0. So at time t, if I want to write the charge at time t, and that is a standard case if the charge was initially 0. So at time t, the charge as a function of t is given by EC into 1 minus e power minus t by tau, and obviously tau is equal to RC. And I at time t, I is equal to obviously dq by dt. Dq by dt, obviously basically we have to find the maximum charge and the maximum current. Maximum charge will be when that will be fully charged, so that the Q max from here would be, obviously this charge will get accumulated, and the maximum charge will be EC. And the maximum current you can get from here, and obviously this maximum current is at the initial moment. So at the initial moment, because when it gets started charge, or starting charge flow will be the fastest, so you just differentiate it, and that will be simply E by R, because all the PD will be taken by this, and no PD on the capacitor initially, and you will get this by differentiating also. So this is actually Qi max, not the at general time. So I max is E by R and Q max is EC. So I max that we had calculated, this is a 116.8 into 10 to the power minus 7 and divided by 1.7, and this is in ampere. So if you divide this is not 1.7, this is actually 1.4. So that will be 12. So we got the maximum current 12 into 10 to the power minus 7 ampere. Let's see which option we can get, and that is the option 1. What I've got 12 into 10 to the power minus 7, that is actually 1.2 into 10 to the power minus 6 ampere. And the maximum charge Q max is EC. E we had got 16.8 into 10 to the power minus 7, and this is 5 into 10 to the power minus 6. So that is going to be 84 into 10 to the power minus 13. So we can simplify this to 8.4 into 10 to the power minus coulomb. So we got two options correct, which are option A and option C.